guys, hope all of us are doing fine. I'm Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the last bit of the various quantum numbers which we had listed. And this, of course, as we said, they are going to be giving us information on various orbitals, and of course, using the particular quantum numbers for the principal, angular, magnetic, and lastly the spin. Now in this case, of course, I had said additionally, apart from orbitals, we are going to also describe the electron in using the 4 quantum numbers. And of course, those are going to assist us in describing the energy orientation and particularly the shape of various, of course, orbitals, which are going to be discussed in this particular case on quantum number and the shapes of various orbitals. Now, the spin quantum number was proposed by George Uhlenbach and Samuel Gaudsmit. And of course, this is going to be very fundamental for us in trying to, of course, describe the angular momentum quantum numbers and the spin quantum numbers, of course, which I'm going to give later, perhaps in terms of an equation. And we're going to explore the relationship between the two, so that in case we come across them in our various discussions, it's going to be easier for us in trying to represent them. Now, as I've said, this was described by Uhlenbach and Gaudsmit, and of course it was designated using this specific letter S. Now, from our previous discussion, I've given basically a algebraic representation for various quantum numbers. Now, for spin quantum number given as S, this is going to assume the values of a positive half or negative half given as such. Now, in a sense, we're going to describe this orientation as a negative or positive, or clockwise or anti-clockwise given as such. So therefore, we can as well describe this spin, as I've said, using those two specific descriptions. And of course, the values are going to range, or specifically the values are going to be either a positive or negative given as such, which is going to denote the rotational direction of an electron on its axis during movement within the space of an atom. Now, in this particular case, I mentioned from our previous discussion on the concept of a quantum, or rather the concept of azimuthal quantum number, and I've said that we can represent the orbital angular momentum using the value of h over 2 pi, and this one was multiplied using L into L plus 1, if I can be able to remember that. And this, of course, was just a root, so we're going to have this one represented as this. So this is going to be orbital, so this implies orbital angular momentum. And of course, this was given in this specific designation. So in this case, if we're going to describe a spin, we're going to have a version of this particular representation given in terms of the ratio of h over 2 pi, and then we're going to have this one s over l, sorry for that, s into s plus 1. So basically, we're going to substitute this particular aspect of angular momentum quantum number using the spin quantum number given as this. And this is going to represent what we refer to as the spin angular momentum given as the spin angular momentum. So in case we come across various discussion whereby we're going to use this or either of these two representations, basically I presume that we're going to create a contrast between the two, which are going to assist us differentiate between the angular momentum, of course, and the spin, or of course the spin angular momentum, and of course the what we refer to as orbital angular momentum given using those two specific representations. Now in this particular case, we're going to see a unique case for this specific third or fourth spin quantum number, in case we list them from the principal, the angular, the azimuthal quantum number, the magnetic, and lastly the spin, in a sense that it is not going to be an integral part of the solutions which are going to be obtained from the Schrodinger's equation. Now, I've mentioned that the Schrodinger's equation is going to provide the solutions which are going to be describing the various orientation, energy, and of course various aspects of an electron within the orbit of a nucleus. And in this case, we're going to see all the orbit of it's going to be the nucleus, electron, system given as such. So in this case, the spin quantum number is going to be unique from the other three, in a sense that it's not going to be a part of or the result of the solution of Schrodinger's equation solved for the hydrogen-like atom, which we have looked at in some of our videos. In this case, that's going to be creating a contrast for it, and of course it's going to be elaborate for us, and especially in trying to have it simply being described from that specific description I've given on the board. Now in this case, the 4 quantum numbers are going to be assisting us in trying to describe various orbitals. And of course, we're going to see that these specific orbitals, as I've said, are going to assume various orientations. And from there in, we can be able to describe the various aspects like distance, energy, and particularly the number of electrons which are going to be contained, and in other aspects, the energies of the subshells, which I've mentioned in some of my videos. So check our description boxes for various links of other videos which we are going to do. And of course, there are going to be concerning various videos on the concept of quantum mechanics, which are going to assist us understand these various topics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.